My name is Michael Pardue. I'm a senior software engineer here at Accusoft, and I'm the self-proclaimed chief T-Rex artist. I go around drawing T-Rexes on everyone's whiteboard. I didn't say I was good. So, the reason why I'm doing this talk, this is about functional programming. Some of you may have used functional programming in various languages and whatnot. JavaScript isn't actually a functional programming language. But what I'm trying to do here is introduce you to a way to structure your code so as to build your applications in a maintainable, reliable, and safe manner. But why JavaScript is awesome? Well, it's powerful and flexible. Really, any type of programming methodology you want to apply to the code is great. So if you want to do object-oriented programming, you can do it, sort of, as long as you stick with prototypes and everything works great for you. You can do mix-ins, which is super cool because people create their objects and you can override all their functionality and you can do what you want to do rather than what they thought they wanted you to do. You can do imperative programming, and that's just normal programming, which ends up everywhere. And of course, functional programming. But the reason why you really want to do functional programming is because JavaScript, it's easy to shoot yourself in the foot. I tried looking for some awesome images about shooting yourself in the foot, and I couldn't find a decent one, so I attempted to draw one. All right, thank you. All right, so one of the major issues with JavaScript is the notion of side effects. You have them in loops, particularly really scary recursive loops, and you have them in asynchronous processes where multiple callbacks are sharing state variables. So I want to go into what a side effect is. A side effect is basically when you are operating on code in a given function, and then you move on, and then something else uses that that variable, and then unexpected stuff happens. So let's look at a sample. I can do that. Probably can do that. Wait, I need everyone to still look at me. All right, okay, so let's kind of go into what this code is doing. This is basically just going to run a little async function. I'm simulating, JavaScript calling like a service with just a set timeout. It's not doing a whole lot. And it's going to execute, and it's just going to increment a number asynchronously, so it's going to continue to call itself. Think back to the recursive looping. So we're going to run that. Oh, yeah, that was super exciting. So we have the 10 digits. Everything worked great, right? But then what happens if all these guys, like this. All right, so we're going to call it multiple times, and they're going to work on this. They're going to call increment, and they're all going to do the asynchronous service and all that other fun stuff. We run it, and it behaved exactly the same. And so why was that? It's because they were all sharing the same incrementer. The scope of I was shared with an increment, and when it was incrementing I, it absorbed it. So let's fix that. With a new version. All right, so let's go into what this is doing. So this is still calling increment, but the major difference is that I am passing I into it. And that means that now I'm not going to be making any modifications in any shared state. The value of I is always going to be the same value of I for that context. And then when I pass it in again, I'm only passing in a new value for what will be the new I within the function. So I'm going to execute it like this. No. I'm going to execute the right one. Still gonna, okay, there we go. All right, so this is an example of where functional programming principles can really help you. So we want to make sure that we're not mutating state outside of the scope of our function's code. So whenever we made a change in here, so this I+1, we didn't mutate anything outside of the function, and this means that it is more provable and safe. All right, so let's go back to the thing. All right, callback hell. Now, you wouldn't necessarily think about this in the functional programming experience, but the biggest thing to worry about when dealing with callback hell is the scope and locality of the variables. So a lot of times when you write callback code, you'll have a number of functions inside your parent function, and you'll be interacting with those variables across all the callback functions. And so that means that it's very difficult to ascertain what the current state of the function is as you are executing your callbacks. All right, so I made another sample for this. And it's kind of I need a little more room. Can you guys read it over there? Are those okay? All right, so this is super scary code. Again, I'm simulating running a request and whatnot, but I am mutating a state variable across all these functions. And it's difficult to totally understand why the code could be doing what it's doing and where it's doing what it's doing, because the state is being shared across all these callbacks. And this is runnable, although it's kind of silly and contrite. Side effects, callback, execute. So it succeeded, everything is great. But the important thing is to take note is that we can't really follow this code. It's difficult to tell who's owning the state variable at any given moment. And so again, functional programming can help, but it's a little, and the biggest thing to take from it is that each one of these functions has what the current state is at any given moment. So this is now a testable function, whereas the original function was not testable. These things are all buried within do somethings. These are all using a state variable that's effectively global to all the callbacks. These are all using a state that has been passed into it. So there is no state that's being shared across these functions. These functions stand on their own. They are immutable in terms of the fact that there is no shared state and they are not modifying anything. And it will behave exactly the same, sort of. There's some random stuff to it because I was making it fun. Right, okay, so anyways, sometimes we are awesome, but most of the time it's just aw. All right, so basically the thing to take away from this is that we need to make sure that the state is always passed in. There's no unreasonable dependencies. There's no scope being changed. What's inside the function is only what's inside the function, and we're not pulling anything from a global state. So why do we want to do this? Because it's difficult to understand the code if it's difficult to understand what the variables are doing and what's changing them. It's difficult to understand how to modify the code because we don't necessarily understand the repercussions of making the change. And I said that. And basically the idea is that we want to get away from unexpected results. We want to make sure that when the functions are executing, they always execute the exact same way. We want to make sure that state mutation happens at the highest level. We don't want to make sure that we don't want the functions to be modifying the state at the lowest levels and at the highest levels. I mean, there's some issues with performance when you do that because now you have to like try to pass in all these references and we have to make sure that we have the same values going across, and there's maybe a lot of memory that's being consumed that we don't want to necessarily consume. But that should be a decision that's being made for those reasons and those reasons alone, not because it's easier. We want to make sure that the dependencies are passed in. And the reason why we want to do that is because that means that we can use the function elsewhere. We can use the function in more places. This is a quote from John Carmack. "The real enemy is unexpected dependency and mutation of state, which functional programming solves more directly and completely." And really, he's just saying that the most difficult thing to debug in the application is when things are happening unexpectedly. I mean, we all know about Heisenbugs and all those other things. This is how we try to get away from that. We have functions that run the same way regardless of the input. So if the input is 1 and 2 and it's going into an add function, it always returns 3. So I'm going to define what I'm considering functional programming. And that's a paradigm where computation is performed through expressions, avoiding state change, and mutable data. And there's a lot that goes into functional programming, and some of it is about monads and other bits. But really the idea that I want to drill home is that this is about trying to make your applications safe and reliable and easy to maintain so that you can change features, you can fix bugs, and you can be confident about the changes that you're pushing out. That makes it more releasable because you can push out faster. You can push out changes faster with your confidence. So it's safer and provable. A lot of functional functions map directly to given proofs. And so it's easier for you to say, okay, this function will always behave in this manner. It's easy to test and validate because now you don't have to build a mock. I mean, one of the hardest things to deal with when using Node.js is trying to mock the different node modules for HTTP, the file system. You're trying to get in there and you're trying to inject your way through all the callbacks so that it doesn't hit the file system, it doesn't hit I/O, it doesn't hit networking. You're trying to bypass all that and just get to your logic. So if you're focusing on a functional programming paradigm, then that allows for you to build a function that is going to only be handling the logic. All right, so another aspect of functional programming is the concept of pure functions. And a pure function is a function whose result is wholly dependent on its input and will always return the same result without side effects. So, I mean, that is kind of unreasonable with JavaScript or in any applications because we need I/O, we need user input, we need to modify the system somehow, we need application state. But this is something that we should strive for and we should work towards putting our logic into. So another thing to take from that is that any function that calls a function that is not pure is by definition not pure. So once you hit a resource, you've basically made your whole call stack ill. So it's contagious. It's like a virus. It infects all your code. So the thing that you want to take from that is you want to pull all the kind of like gluing logic up to the highest levels in your function. So all your business logic is as far away from the resources. You're passing the resources into the functions. You're passing any form of I/O into the functions so that the functions themselves are not actually making those state changes. So one of the benefits of pure functions is the concept of lazy evaluation. And that's because you can make assumptions on what is going to be executing. And so lazy evaluation is just simply the execution of code after the fact, after you've defined the variables and after you've defined the functions. It's not native to JavaScript because JavaScript doesn't have any mechanism to facilitate it, but you can implement it. So here's a version of it running within JavaScript. So here's a function that follows the functional paradigm. All it is taking inputs A and B, and it returns A plus B. For those of you who are unaware, this is the ES 2015 arrow functions. And so this is just saying, this is just a sugar for the function definition. So this prepare function is going to take a function f, and it's going to take a list of arguments. Again, this is ES 2016, but this is saying that this is going to be params, and the definition of this function is saying f comma a comma b comma c comma etc. And then this returns a new function that will, when executed, pass in the arguments that were originally passed. So this prepare function is executed, passing in the callback to add, and then passing in the parameterization to add, and it builds a function that will be executed later. And so the benefit of this is that now we can kind of prepare a plan and then execute it way later. And so you can make optimizations based upon what you are going to actually execute. And so when it executes, it returns 3. But one of the biggest things about pure functions is that they're reproducible. And so this is a concept called referential transparency. Basically, the referential transparency is just saying that given inputs A and B, you always get result C. It helps with unit testing because you can make more assumptions when you're writing the unit test. You always know it's going to follow an exact code path. You always know that it's going to behave the way that you're expecting, and so you don't have to handle as many mutations through the system. The reproducible aspects of pure functions allow for memoization, which is basically just saying that you can safely cache the values. And so if A and B always return C, then you can just basically cache the definition so that whenever you call A and B again, it always returns C. And this improves performance for using functional programming so that you can get past some of the memory requirements or the CPU issues for having the additional layers of functional stacks. So I have some examples. All right, so the first thing is the Fibonacci sequence. So the first thing that I want to show you about this is just that all the input that's going to be used to modify the execution of the function comes through the arguments. There's no global state. There's no shared state. It's not modifying a global variable. And then once again, just the normal ES 2015 arrow functions. This little thing here is doing a spread. So basically it says that as this returns an array, just concatenate it to this first guy as though this first was wrapped in an array. And then it builds up an array. So I'm going to execute this. If I can spell Fibonacci right, but thank goodness for tab. All right, so it executed, and that's great. But this array is kind of ridiculous, so we're going to run this version of it. And so what this does is it's only going to return the last value, but what this exemplifies is the effectively constant nature of a pure function. All right, so whenever the Fibonacci function is called with 10, it always returns 34. That is always going to be the case. And this is provable, through this function. We can write down a proof if we wanted to. And that'll always be the case. And if you take that to other bits of logic that you need within your application, you can make that same assumption, and then you can build off from there. So let's look at implementation of memoization around it. So this is what this is doing is this is just this is just a really silly math thing I was just trying to get it to go for more than a few microseconds while I was executing. But basically to show the difference in time. But what this does is this kind of takes the prepare from the original lazy evaluation and gives a little bit more work where it caches for the definition. So when I create this function, it's going to build this guy right here, and it's going to be sharing this value with this function that's being passed out. And so when it's executed multiple times, it should retain the existing value. And we get to do this because we know that given A and B, it'll always produce the result to this silly function that really isn't going to do much for us. All right, so I'm going to execute it. And so if you look here, let me make this bigger. If you look here, the first time it ran in 0.14 seconds, and the second time it ran in some number that's not 0, but it's close enough to 0 that that's what it decided to give me. But basically, because of the relatively constant nature, the memoization principle and whatnot, we're able to do this. We can't do this if we're relying on external resources. We can't say that this will always behave the same if it's going to go and hit another service. So functional programming lets us make more assumptions, and it gives us safer code that allows us to write more performant code. And the other benefit with this is, like, say we're like building a game and whatnot, and we're throwing a lot of values in to like calculate some vertex and everything. We can run these prepare statements in such a manner that we kind of build up the new values. They're on the fly. We don't necessarily know what the constants are going to be. These could be changing values. But then we can maintain these and call these multiple times. All right. So by definition, applications cannot really be pure. But we should reduce the functions with logic to pure functions whenever possible. And we should make sure that we make high-level functions glue pure functions together. And so all I'm saying with that is just like, so we have a request handler, and the response comes in. All the bits that are hitting the service should be at that highest level. And then anything that's like concatenating strings, running some sort of mathematical function, anything like that, should be further down and glued together with the output from the services. So a little more about state mutation. Oh. Well, okay. Not sure what happened there, but I just wanted to comment on state mutation and just again say that when we're talking about state mutation, that is the change of the application in terms of like what your session is currently doing. So if you have some user and the user has hit such and such button and then is expecting to go to the next page or something like that, that would be your session. And you want to make sure that the input of like where you currently are and all that business is passed into each of the functions rather than making use of a global object. And that includes a session object, and keep that outside of the functions where you're handling all your logic. Okay, just a little bit about promises. I'm not going to get too deep into promises, but one of the benefits with regards to functional programming is that when you take code that's been written like normally for Node.js with the callback structure and whatnot, the definition does not lend well to function of x returns y. Instead, it's function of x with like another function composed with it. This means that we can write composable code where we can take the function and pass it into another chain of functions. So here's an example of how it's fixing it so that we can treat it as a proper function. So the get something is taking some params ID from the request object, and then it's passing in the callback, and then you're taking it like this. And this is where we get the chain of callbacks, where we dive into callback hell. And instead, if we do something like this, now we have a function where we can say that given x returns y. And so we can always say x returns y. And so this always returns a promise that hopefully will resolve appropriately. Expressiveness is a big part of functional programming because expressiveness allows for you to understand the intent of the function a lot better. So as your smaller functions with all the logic are written, you can take advantage of various stylistic aspects of the language that allow for you to minimize the amount of code that you're actually putting together. Usually you want to reduce the branching as much as possible. So you want to pull the branching up and out of your logic functions and put that with the glue. And you want to reduce to as few lines as possible. This is only possible when you're using the syntactic sugar that is associated with various languages. So arrow functions help, and here's an example. So f of x equals x times 20. This, when you look at this, it doesn't flow well. You can't really say f of x equals x times 20. You're compelled to say the function f of x is going to return the value of x times 20. Whereas if you use the syntactic sugar, you're able to say a lot more natively and naturally, f of x is equal to x times 20. It's a lot more natural. It's a lot easier to see it as an actual equation, and it's easier for you to treat it accordingly. And I want to reiterate that your function should be stateless and that all state should be passed into the arguments as arguments into the function, and that globals are bad and are totally antithetical to this, and to not use variables from the parent function scope. All right. Unless you're in a special little function that looks like this. But this is a special function that would be built into as part of your API. All right, so let's go into stateful. So here's an example of a stateful application. This is kind of natural for
You broke him. He's blue screening.
All right, so this is a natural way to write one of these functions. You know, you prepare your list of callbacks for your promises, and you interact with the services to kind of hydrate all your variables and pull all your data in. So this is kind of a mock-up of a handler for listing all the users' posts to some forum or something. So we have a token, and then we're going to need the user ID, and we're going to need account info, and we're going to need to get the actual list of posts so that we can get it back out to the user. So we'll get the user ID first, and that goes and gets the user ID, but now we got to do something with the user ID, so we save it into this variable. And then we go and fix a bug. So then we call the get user info because we need all the account information with the user ID. And then we, again, need to do something with that account information, and so we store it into another variable. And then we need to actually list the posts. So we get the post from the post service, and again, we need to do something with it, so we put it into a variable. And then finally, we can prepare the posts. So then we go and we, for each of them, add in the full name, because when we render the stuff out to the HTML, we're going to want the full name for the account rather than the user ID. And so the problem with this is that, again, we're calling all these functions, and we are saving the variables to a state that's shared across all the callbacks, and now all these functions aren't unit testable. They're they're buried within the handler, and we can't test them very easily. Let me save this so that I can put it up to GitHub.
You're missing a parenthesis.
Yeah, get user info, the thing you edited.
Ah, thank you. All right, now it's better. All right, so let's like what?
You pass code review now.
All right, so let's look at a stateless form of this. All right, the first thing that we want to do is when we actually execute the code, we want to project the values forward through the system rather than try to like reference them as we are saving them. So all this is doing is this is just taking advantage of functionality within the promise function, the promise class, which is in the Microsoft, sorry, not Microsoft, the JavaScript API. And so I built an array, and these get account infos are returning their promises, and then all is going to wait for both of them to succeed with the objects. And then I'm going to pass them into the prepare posts. And so now we look at, and this is just retrieving information. We didn't actually need any functions to get that information to call that business. This is just glue. This is just getting all the resources from external sources and getting those ready so that we can actually do the processing. So now I've moved the business logic into its own function, and all it cares about is an account info object and a list of posts that have been passed into it. There's no external resources. All it is just the execution over the list of posts and applying the account info to it. And then rather than mutating the array, I'm going to call the map function from array that's on the array object, and I'm going to build a new array. So now I'm not mutating the list of posts that have come from the list post service. I am only returning the array that I want to give back to the users so that I can render the HTML. And so this is unit testable. We can pass in any number of account info objects and post list objects, and we can be guaranteed how they're going to execute. We don't have to worry about external resources. We don't have to worry about whether or not the service is up. We don't have to create a mock. We don't have to create anything. We can just run this little bit of business logic through all the unit tests, all the permutations of the data, and we're golden. And then, of course, it carries through all the promise chains, and we get it back into here, and then we're able to get it back out to the users, and everyone's happy. And if we wanted to make a new change, because we forgot to put the title for some reason, adding that and then modifying the unit test for that will be super simple. Okay, so let me go back. All right, so to reiterate, functional programming, when you're applying it to your code, is expressive, it's stateless, and it's without side effects. I already did that. All right, so I just want to go into a little bit of JavaScript and arrays, because the array functions are generally apply the functional programming techniques. So all the functions take the form of f of x returns y. So whether it's filter, map, reduce, left reduce, sort, you're taking one of the items and you're returning either a Boolean, a new object, or some other value. But the idea is that the result of executing any of these array functions is that it's returning a brand new array. So as long as you as the developer behave and don't try to make changes within the callback for each one of the functions right here, you don't have to worry about whether or not your list has changed. And any code following that wants to use that list can still use that list. So just to dive into map, the map is really good because it produces a brand new array where you have transformed items. So you're creating a new object, you're creating a kind of a subset of the item like I was doing in the stateless form in the example. And again, the array is unchanged. So here's an example. I have taken an array of integers and I'm going to run this function over it. It's very clear what this function will do, mostly because it's descriptive like that. But it's going to return a new array where multiply by 2 has been applied to each one of the items. And so that returns 2, 4, 6. But the benefit of doing it this way is that multiply by 2 is unit testable. And so you can pop this out of whatever logic you're writing, and then unit test only this. And then when you go to unit test the glue function around this, you can skip over trying to test all the permutations of this and trying to make sure everything's okay, because you're able to just focus on this rather than trying to figure out how to generate this array. And filter, applies the predicate to each item and then returns a new array. But again, just to further drill that in, this is unit testable, and it's been separated out, and we didn't permute this array. This was not mutated, it was not changed, and we can make assumptions about how this is going to be later on, because we don't have to worry about whether or not it was the same array or any business like that. All right, reduce. Reduce is a funky function. Some people have difficulty with it. I know I had difficulty with it for a little while as to trying to figure out how to really understand why to use it, because a lot of the times when you use it, you're just, like, all the examples are just like, oh look, I'm going to make a sum of all these numbers. Why didn't I just use a for loop? So the reduce function does exactly what it says it does. It's reducing a list to a single result. It performs an operation on each item and carries the result to each subsequent item to then again perform the operation yet again. So this is a quick example of how to use it. We have this string and we want to find the count of the word the for some reason. So we generate an array from the string, and again the string is immutable. The array that we produce is going to be immutable, and then we call reduce, and the function here, this doesn't have to worry about the fact that it's going through an array. All it's saying is that what was the last total and whether or not this word is going to be the. So as reduce iterates over the array that was created from this, which is just an array of the strings the, quick, brown, fox, jumps over the lazy dog, it's able to produce the count of the word the. So then it goes through here and it just says if word.toLowerCase equals the, then return a 1, otherwise return a 0, sum that against total and return that result. And then that result is what gets passed back into total, and then word on the next iteration. Oh, I didn't put it here. So I'm going to run it for you guys so you can see it. There's the code. Node, arrays, reduce.
So have you found places where you use that besides trying to sum? list the numbers instead of using a for loop?
Yes.
You can build pretty much anything with it.
Right.
That's kind of like the magic of it. It's not just accumulating or
Right.
reducing things down. You can literally create a new object or a new array.
Right, but
Right.
What's a practical use? Where have you used it?
So I've used it in our metric handling stuff where, again, it's actually incrementing numbers, but what it's building is building a set of the kind of like the usage within our system. So it's coalescing, multiple sources together, and it's building a representation of the usage over a given time period. But the idea is just that given this set of data, I can produce a new object, but a single object that is some form of representation of the coalescing of all the items within the system. But again, the thing to take from it is that this is unit testable on its own. And so it gives you a lot of confidence for the usage of this function elsewhere, and it gives you, confidence that when you run it over any string or anything, it's going to behave appropriately in how you expect. So I just wanted to make a quick mention about the real world and say that one, I/O is a side effect. When you have a server that's running and listening to HTTP requests, you're producing an output, you're changing state, you're interacting with the system. So you can't have pure functions. It's all about trying to get as close to a pure function as possible. Again, all asynchronous functions are side effects, and totally pure applications would be useless. This is about trying to make your applications more robust. This isn't about trying to make your applications perfect. You can't make a perfect application. It's about trying to be totally confident in what the current state of the application is and totally confident about how your functions are going to behave to given input. So you want to reduce the state as much as possible, and that's it.